Good afternoon, everyone. Thank you for joining us. My name is Katie Rowley. I'm with the NOAA Central Library hosting today's webinar in conjunction with the Tiffany House from the NOAA. Tiffany, help me out here. You're with the Technology Transfer
Partnerships
Office. Partnerships Office.
Yes.
Okay. Everyone online, we do have a great presentation for you. Logistics, if you have a question, please place that in the question panel and we will get to that at the end of the presentation. If you do have any sound or quality issues, we recommend that you try logging off and logging back in. And with that, I'm going to turn it over to Tiffany to introduce our speaker.
Thanks, Katie. Good afternoon, everyone, and thanks for joining us today. My name is Tiffany House, and I am the Commercialization Specialist for the Small Business Innovative Research Program for NOAA. NOAA provides competition-based awards to small businesses for research and development to transfer their innovative ideas into commercial products. The research must meet the objectives of the agency. Today, you will hear from Mr. Kevin Sullivan. He is the CEO of Toyon Research Corporation. He is in phase 3 of the SBIR program. In this period, his phase 2 innovation moves from lab to market. The small business must find funding in the private sector or other non-SBIR federal agency funding. Today, you will hear from Mr. Sullivan. Mr. Sullivan has recently applied the knowledge gained from DoD applications to the semi-automated detection of marine mammals using infrared video. He is currently leading an effort to create a vessel-based camera and processing software that can provide 90 degrees of coverage to monitor the ocean for the presence of marine mammals. During this webinar, Mr. Sullivan will tell us about his NOAA SBIR funded project and how it has been developed. I want to give Mr. Sullivan time to speak without delaying this any further, so it is my pleasure to introduce Kevin Sullivan.
Hello, thank you, Tiffany. I will be speaking today, but there's a number of people that both at Toyon and within NOAA who have helped this effort. Most notably at Toyon, Christina Wright and Mark Fennell. And most notably at NOAA is Dave Weller and Wayne Perryman. Dave, I believe, is also on the line today. And Dave and Wayne basically started this effort back in, I think it was the 2012 SBIR round. And they were working on abundance estimates for the gray whale migration and wanted to look at ways to add some automation to that and the ability to perform that operation at night as well as during the day. So an outline of my talk is, first, I'll talk about that SBIR, where we built a system, a prototype, to perform semi-automated gray whale migration statistics, or basically counting the whales as they go by. Say a little bit about how we detected them and some processes for counting them. And then I'll go into what we did after the SBIR. And as Tiffany mentioned, that's more the phase 3 process, and where we received funding mostly from oil and gas organizations to do some additional shore-based detection of whales, as well as moving to a vessel where the cameras are moving and there are some other constraints because of that. Then I'll finish with a quick summary. So first, talking about the SBIR a little bit, one of the things that we had to do was develop an algorithm that could automatically detect gray whale blows observed with infrared cameras. We wanted to be able to count the whales at night, and so that required the use of infrared cameras. We built this algorithm in C++, and we were able to process 3 video streams on a single desktop computer in real time. In good conditions, we could detect whale blows over 7 kilometers away. More typically, probably 5 kilometers was the limit. And of course, when it was foggy, we had almost no ability to detect whales. So there's pretty much a spread based on atmospheric conditions. But from an optical standpoint, the limit was in the 7-kilometer range. We also created a forensic tool for processing the blows that come out of the detector. So these cameras will operate for extended periods of time, months. And so while that's happening, there's all sorts of things that can show up, such as birds diving in the water, or birds in the air that kind of all of a sudden swoop up, and other marine mammals, such as dolphins of various species that go by. Also for us, because we wanted to count whales, we didn't want to count the same blow twice, and we didn't want to count the same, breath. And if we detected the back of the whale or the tail of the whale, we didn't want to count that as a blow as well, because in our counting software, we're using knowledge of the respiration statistics of the whales as a part of the information that was used to count them. So for instance, if we saw 2 blows closely spaced in time, we would know that that must be 2 animals. And so there's a whole process on the computer for keeping track of that. And it's a process often referred to as particle filtering, which can take into account the dynamics, the motion of the whales and their spacing, as well as knowledge about their respiration statistics. And so we built a tool that after a human works through forensically through the whale blows that are automatically detected, those filtered blows go into the whale counting software, which then makes does some inferencing in terms of the motion of the whales and the respiration statistics, and comes up with an estimate of the count. Now, we installed a functioning system at the end of phase 2 with 3 infrared video cameras and a computer, and it's collected months of data, and we've looked at quite a bit of data numerous times and compared it to human counting, both on the video and live, and I'll show you an example of that in one of the future slides there. First, just for those of you that aren't familiar with where Granite Canyon is located, in the upper left is a map from Google Earth of showing the location of Granite Canyon. It's basically a little bit south of Carmel and the Monterey area. If you look over on the right, that's a zoomed in image of the facility. It's basically just off Highway 1. And then in the lower left is a picture of 3 infrared cameras that were used, mounted outside, and there was a cable that went underground into that building behind it. And in that office there with the window, there was a display in there that you could look out the window and then also look at the computer display of what the cameras were seeing. And in the lower right there is just the initial setup of the system there. That's the power supply being hooked up and the conduit coming in with the video feeds. Okay, so what you would see in the display inside the office is what's shown here. Across the top of the image is the video from 3 cameras. The fields of view of the cameras were different. The center camera had a narrower field of view, and we did this somewhat incrementally. We weren't sure how far we could detect the whale, so we got a narrower field of view first and looked to see if we could detect whales, and we could detect whales at a very good range. The whales predominantly migrate at about a 2.5 kilometer distance offshore. And so our goal was to at least get 3 kilometers. And of course, as I said earlier, we exceeded that even with a wider field of view camera. Now, there's a real benefit to having a wider field of view, because the goal here is to make sure that you get at least 1 blow from each whale as they're passing by. And they're typically passing by north to south or vice versa. And so the benefit of that wider field of view, again, is to catch them, especially if they're traveling closer to shore. Now, in the upper right part of this image, you can see an example of an automatically detected blow. In this particular day, the conditions were quite benign. There isn't a lot of white caps. There's maybe a little bit of haze. The water's a little bit washed out, but this particular blow is showing up very nicely and detected very easily. On the bottom part of this, you can see a map display. And this shows the process of estimating how many whales are going by. And so what happens is as the whales travel, in this case, I believe they were traveling from the north to the south, we get detections on them. And depending on how many detections we get and the timing, we do some inferencing with the particle filter, and we create a probability mass function of how many whales are in that pod. So in this particular case, you can see the peak of the PMF is at 1, so we think this is most likely one whale traveling by itself here. There is some chance it's more, and as the whale travels through the field of view of all the cameras, we will get additional detections possibly, and that will help refine this estimate of how many whales are going through. And that's the reason why you'd like to have as wide of a field of view as possible, so that you can basically accumulate evidence over a longer period of time. Now, when human observers operate here, they'll often look a little bit to the north of where these cameras are looking, and of course the humans have a much wider field of view potentially than what the cameras are looking at. This is a screenshot from the detector that just shows a closer view of a couple of whale blows that were detected. On this slide, I'm going to describe a comparison that we did. There was a group of observers that were basically humans that were on station with binoculars, and they were counting the whales going by as they've done historically for an extended period of time. And they created their count, and so you can see in the lower left graph is basically their count versus time during the day, and the vertical axis is the number of whales, and they got a total, they estimated 47 groups and a total of about 85 whales. There was a period of time during the day where they were off effort due to there was a thick fog that came in, and so basically they went off effort for a little while. In the graph over on the right is what we obtained in a semi-automated fashion, and basically we had the detector automatically detecting the whales. We had humans that filtered all of the detections to limit it to just one whale blow per whale, and then those detections were fed into the automated counting software, and this graph is the output result. And so you can see the graphs agree with each other to some extent. At any given time, they may not agree, but in aggregate at the end of the day, we ended up with about 90 whales with the automated method, and estimated about 45 groups. And there's some, expectations for why these would differ. As I said earlier, the humans tended to look more towards the north and had a wider field of view. And so the timing is going to differ a little bit from when they see the whales and make their determination and when the machine does. But overall, we were pretty pleased with this result, especially early on in the development of the system, that we were pretty close there, when looking at the result over a whole day. Okay, now I'm going to talk a little bit about some of the things we've done after the Phase 1 and 2 SBIR, and the NOAA staff, in addition to giving us a good education and during the SBIR, have also collaborated with us after the SBIR, and they're still working with the system that we developed on the SBIR, and we're continually making updates to it, and we've been sharing our detector with them as it evolves and slowly gets better and better. Okay, so some of the shore-based activities we've had after the SBIR is we did some observations up in the St. Lawrence River. Up there we saw minke, beluga, and finback whales. And again, we're solely using Longwave IR cameras because of the low cost of those cameras. One of the things that was interesting up in the St. Lawrence River is for the first time we observed whales where the observed skin temperature seen in the infrared imagery was actually colder than the surface water. And our theory or guess on that is that, well, these whales were diving deep down where the water was much colder and then coming up to the surface, and so their skin temperature was still a bit lower than the surface water temperature, and so that was why they were showing up as colder. All other observations we've made, the whales have always, their skin temperature has shown up as warmer than the surrounding surface water. So that was kind of an interesting observation we had there. Vista Point in the Santa Barbara Channel, we did a number of tests there, and it's predominantly gray whales that we see there. Also, we've seen some humpbacks, but it's mostly gray whales. We did do some comparisons with observations and satellite images, as well as some drone images. And we also compared shortwave infrared to longwave infrared imagery. And I'll show a picture so you can see a comparison of that. We also did some observations in Point Arenas, California. And the challenge there, it was very windy there. And so that was the big challenge there. We also operated at night at Point Arenas as well as during the day. And a big effort that we had was on Sakhalin Island, where we observed western gray whales for several months with longwave IR cameras. And in this case, we wanted a wider field of view. And so we had 9 different cameras on a structure covering 90 degrees. And we were supporting some oil and gas operations out there. So on this slide, I'm going to show over on the left is a shortwave infrared image, and on the right is a longwave infrared image, and that's the same whale blow that is circled in both of those cameras. That island you see in the background is Santa Rosa Island, and you'll notice in the shortwave image, you can see quite a bit of detail on the island, and shortwave is known for being able to cut through haze. In the longwave image on the right, you can barely make out the island but not see much detail. This led us to think, well, hey, maybe we can, in foggy conditions, we can extend our range a little bit with the shortwave. We subsequently did some tests, and there are times when you can do a little better in the fog with shortwave, but it's predominantly kind of an all or nothing thing where if you can't see it with longwave, you can't see it with shortwave either. So that was kind of an interesting observation. But when you have a condition like on this day, where it's a finer particled haze that you have, then there is potentially an advantage to the shortwave. Another disadvantage of the shortwave is unless you have a lot of moonlight, it doesn't have that low light ability of the longwave, which is more of an emissive type of a sensor. Okay, so the detector has evolved over time. This is a more recent view of that detector. Again, here we're showing 3 different cameras across the top. And there is a tool that I alluded to earlier, which can allow you to forensically filter through the detections that are automatically made. And what happens is there's the text over on the left tells you what time that particular observation is from and what camera it's from and where it was pointing and where it thinks the whale detection is located. And over on the right there, that larger screen basically shows a box where the alleged detection is located, as well as it'll play a short 8-second video clip of what it thinks is a detection. So an operator can go through here and very quickly, just click with a mouse yes or no on these things, and it'll color code them: green for yes, that's a verified blow; red if that is, either a double detection on the same blow, or part of a whale body, or a bird, or a dolphin, or a whitecap, anything that we don't really want to count as a single whale blow. Now, the other thing to note is, in the case of counting whales, you want to be pretty particular about just one whale blow per whale per breath that it takes. But in the case of just wanting to know about the presence of animals, then a lot of these detections are actually of value rather than believed to be, treated as false alarms. If you just want to know if there's whales present, for example, if you're operating a loud sound source and you need to know if whales are present in a range within danger of injuring themselves, then any blow or any detection on any body part or on other types of marine mammals is of interest. Okay, so at one point we got a lot of interest in doing this from a vessel. And of course, on a vessel, the cameras are moving, and so that adds an additional challenge to the detector, which is basically relying on looking at the same scene in every pixel over a period of time to make its determination of detecting a blow. So one of the things we had to do early on is basically stabilize the imagery. And to do that, we used a low-cost inertial navigation system. The problem with most inertial navigation systems is they tend to drift over time, especially low-cost ones. But in this case, we really only have to register imagery that is, say, a 30th of a second apart, one frame to the next. And so that drift rate, although it's significant for somebody trying to navigate over an extended period of time over those very short time distances, it's really quite good. So the other challenge with vessel-based or even shore-based is you want a wide azimuth sector that you want to cover. And so you're going to need multiple cameras. And when we did the 90 degrees from shore, we had a rather large structure to support them and hold them. And so one of the things we had to do here was shrink that down into a much smaller package and still get the 90 degrees of coverage. And so we've been working on a camera that we've built and began testing last summer, and we're going to do some additional tests this summer. And I'll show you a picture of that on the next slide. And so we are developing this camera that I described, and one of the key aspects of that is having a high frame rate. The duration of the whale blows we've observed as short as 0.2 seconds and as long as 6 seconds. So it varies quite a bit, but if you want to catch those short duration whale blows and you want to get multiple snapshots of them on multiple frames of data, then you want a pretty high frame rate camera. The cameras we're using are 30 frames a second, and I wouldn't go any lower than that. But you also want a large number of pixels on target, and so it's really a pretty stringent requirement on the camera. The nice thing about using the low-cost INS is there's no gimbal required. One of the things we started with initially when trying to do vessel-based was using a gimbal to stabilize things. And a good gimbal that stabilizes well mechanically is rather expensive. And so we went with more cameras and stabilized them electronically with the INS, and that gave us a much lower cost result. And I'll show a picture from a vessel-based detection that was, in the 3 to 4 kilometer range. So this is a picture of that camera that I was describing. There's some CAD models of it over on the left from a couple different perspectives, and over on the right is a picture of the camera that is deployed on a whale watching vessel that leaves out of Santa Barbara, California. And there's 6 imagers in this camera, and it covers a 90-degree field of view. The camera is fairly small and lightweight. It's about, I usually say it's the size of a box of basketball shoes or a regular size shoebox, and a single person can easily carry it and mount it. This shows a snapshot of some thoughts on where we might be headed. The camera module that that with the 6 imagers is shown over on the left. The video from that feeds a computer, which is now running video from 6 cameras and processing it in real time. And that feeds an operator display, which can process the video and also show map images of where those detections are expected to be located. So these 3 elements here, we've got a pretty good handle on in terms of development and have working prototypes that we are testing and developing further. Other things that have been talked about is adding data from an acoustic system, which could also be fed into the computer. And the advantage of that is you can get potentially decent range information out of an acoustic system, which would be complementary to infrared information, which is typically difficult to get range information on, but very good to get angle information, so you get a nice fusion out of that. The acoustic system would also be beneficial when you have fog, because the infrared cameras cannot see during the fog. The downside of a complete acoustic system is the animals don't always vocalize, and so you're reliant on them to vocalize with the acoustic system, and so it might be interesting to put the 2 together and kind of get the benefits of both at one point. We're not currently doing that, but that's one of the things that we've talked about in the future. Another thought is to basically broadcast the whale detections on AIS, and so you could then observe them on a chart plotter. One of the applications that's been discussed is for ship strike prevention. And so if you put these detected groups of whales and put them on a chart plotter in places like the Santa Barbara Channel, where you have a lot of ship traffic, the passing vessels could basically be alerted to the presence of whales. And of course, for that ship strike application, you don't really need the 90-degree field of view. You could get away with a much narrower field of view. On this slide, I'm showing some imagery, some snapshots of some blue whales that were detected with the vessel-based Longwave IR camera. I think one of these was a little over 3 kilometers and one was a little bit over 4 kilometers. This was a pretty blustery day, so you can see there's a fair number of white caps starting to form there. Okay, so in summary, we had although Toyon has received more than one SBIR from NOAA, we were working on a couple of different things. There was a single NOAA SBIR that was launched to basically do this work with infrared cameras and whales. And it's really been a great experience, and I think it's a great example of where the SBIR program did exactly what it's supposed to do in terms of it instigated a number of events and interest in something that would have never been started without the SBIR program. Again, I can't thank Dave Weller and Wayne Perriman enough for getting this started. They basically gave us our education on the biological aspects of this, and they had been looking at applying infrared cameras. Before we came along here, they were using some older Navy cameras, but had already started in this area. We got some initial funding out of the SBIR to develop our first prototype. We were given the facility, or allowed to have access to the facility up at Granite Canyon, and that was a key part of being able to collect a lot of observations in a place where we had power and could collect data for an extended period of time. And it's just been a great experience working, I think, with the NOAA scientists. Now, since the SBIR, we've had many post deployments, in the Santa Barbara Channel, Point Arenas, St. Lawrence River, and Sakhalin Island. And it's interesting that at each one of these places we see different things. It's amazing how much even the same animals, gray whales across California, will appear differently at different locations. We've also looked at lots of different species: gray, minke, humpback, blue, beluga. I'm not a biologist, so hopefully I'm not mispronouncing or misrepresenting any of these species. We have tested a vessel-based system that demonstrated the ability to detect whales at ranges over 3 kilometers. If you really want longer ranges, you can achieve that with improved optics. The field of view of the 6 cameras is about 18 degrees. So we went with a wider field of view to basically use less cameras and cover wider field of view economically. And the effect of that is you get a shorter detection range. If longer detection range is of interest, then you just improve those optics to make them more like what we were using at Granite Canyon. And vice versa. If you want to get wider azimuth, then you just get a wider lens. We have a vision for the future that for how we can operate from a vessel. We're going to be doing some testing this summer up in Canada, and looking forward to seeing the system continually get better. We've come a long way. The NOAA staff showed a lot of patience with some of our early versions, which had issues with video dropping out after a couple weeks from cameras and various things of that nature. But we're gradually getting this thing to work better and better, and looking forward to getting a very robust system put in place as we keep going. So that's all I have to say.
Great. Thank you so much, Kevin. We do have a number of questions online, and anyone who has a question, please place that in the question panel. And I'm going to start off. We have several questions from Ted Elliott that started earlier in the presentation, so they refer to some earlier conversation you were having. The first question is, how many blows do you count for individual whales normally?
I'm not sure what you mean by normally, but I think normally you're thinking for the human observers, and I don't know if is Dave on the line? Can Dave speak, or do you have to transfer?
I'm not sure. Let me check.
Okay.
If David Weller, correct?
Yes.
Okay, I might be able to.
And if not, I can take an attempt. But while you're doing that, I'll take a shot at the question. Basically, it's humans that are detecting, and they're using their own mind to understand, what they're seeing and how that relates to the number of whales. And so, the number of blows that they use, is going to be up to the individual to some extent, but they're basically doing the same process of inferencing that the machine is doing. So, it depends on the person and how many whale blows that they need to accumulate to make their determination. And Dave would be able to better answer that question, but hopefully that gives you a little bit of a feel for it. And for the machine, we want one blow we want one detection per actual whale blow, but we're also doing that inferencing process of accumulating multiple blows over time. And for the machine, you know, if we can get, say, 3 surfacings with 3 whale blows, then that's usually probably a pretty good amount to give you a good estimate on how many whales are present. We don't always get that. If they're traveling really close to shore, it may be less than that. Not sure if I answered the question there, but that's my attempt.
Okay, I did get David Weller on, but I'm not sure if he can speak, if he wants to give it a try.
Dave, you there?
Yes, hello, I'm here.
Hey, Dave, did you hear the question?
I did not, I'm sorry, I missed it.
Okay.
That's
You want
okay.
to repeat?
Yep, I can repeat that. The question was, how many blows do you count for individual whales normally?
It depends on how busy it is with the whales going by. So during a peak part of the migration, we might count 2 to 3, 4 blows in a surfacing, and then we let those whales go by. They've been counted. But during slower times of the survey that Kevin is referring to, when we can actually track animals, we'll track them over multiple surfacings. So we collect something on the order of between 3 and 5 blows per surfacing. The animals then dive, there's a dive time, they resurface, and we try and get back on them with a first surface blow.
Great, I think that answers it. I'm going to move to the next question. Is it just blows that are detected? And are you able to distinguish between different species? How so?
So it is not just blows that are detected. And so one of the jobs of the person that's, you know, basically reviewing the detections is to rule out things that are not blows. So back or tail, we want to rule those out because the counting logic is assuming that each detection is a single blow. We can also get multiple detections on. Sometimes we'll get a really big bright blow, and that'll trigger multiple detections. So we also only want to get one detection on one blow for the purposes of counting. Now, for the purposes, again, of just knowing if a whale, an animal is present, which is a different application, in that case, you don't care if you detect the body or the tail or multiple detections on the blow. You're just trying to determine presence. And so there's a less stringent requirement in that case. As far as determining whether it's a different species or not, that's pretty difficult to do. I think humans are pretty decent at that, but the machine is not set up to distinguish between species. And so if we're trying to just count gray whales that are migrating, then that'll also be something that the human will have to filter out. If they see, you know, Rizzo's dolphins on there, a human is good at making that distinction, and so they will basically rule out the detections from the Rizzo's dolphins. Now, one of the things we are working on is a classifier, which I expect in the not too distant future will be able to distinguish something like Rizzo's dolphins from a larger whale. I doubt it will do a very good job at distinguishing, say, a humpback from a gray whale, but I think groups of dolphin detections versus whales, I expect in the not too distant future we will do a good job of that. Our initial test that we've done with the classifier has been taking some of the false alarms that we've had in terms of birds and things like that and classifying those versus whale blows, and we've had some initial very good results with that.
Awesome. I'm going to move to the next question. Is there a seawater air temperature limit for the camera to be able to detect a whale spout?
I don't know is the short answer, because I haven't seen such a limit. And it's not simply the temperature of the water that matters. You know, for activities like dolphins, it's really the disturbance of the water more than their blow that we actually see that's present. And so when the water is disturbed, its appearance to the camera, it appears as something much hotter, even though the temperature of the water isn't really changing. It has to do with the radiometric properties of the water and how they change when it becomes, more of a disturbance than this flat, smooth plane. And so short answer is I don't know, but I don't think it's quite as simple as you might expect, in that, it's warmer water may be more difficult, but it's not out of the question that you couldn't still detect things because of that water disturbance. And I think also what you're seeing with the blow in the air, I think the fact that it's warmer is part of what helps it show up, but I think there's also this, varying emissive properties that are occurring as well.
Okay, so follow up, you haven't tried the system in tropical waters, correct?
I've not tried it in tropical waters. That's correct.
Okay. So I'm going to find a next question. Have there been any discussions for using the vessel-based systems in place of protected species observers during nighttime operations for oil and gas survey work or in any other industries?
Yes, oil and gas. We have used it in oil and gas operations to look for whales.
Awesome. Thank you. Okay. Does time of day affect the brightness of the blow, thinking of blows front light or backlit?
Time of day, not so much. The one interesting thing is at night is usually generally the best quality of imagery. Time of day, it can affect things a little bit, but not so much. And it also tends to be other things such as, the amount of haze or the amount of moisture in the air it tends to be a stronger driver in terms of how nicely the blows present themselves than time of day.
Okay. Next question. Is all video recorded or only clips during blow detections?
All of the video is recorded, and then that allows us to forensically look at things, years, months later. And so, yeah, we have lots of data, and NOAA has lots of data as well.
Great. Next question. Were the St. Lawrence minke whales less detectable because of their skin temperature?
Not really. It's really the contrast that matters. And so in the case that they appeared darker, there was sufficient change that it wasn't that much more. Maybe it was a little bit more difficult for the same range, but not dramatically so. The thing that would make it most difficult is if they appeared to be basically the same temperature as the water, then there'd be no ability to detect them. And so as long as they're either colder or hotter and there's a difference, that's the thing that will allow us to detect them.
Okay, thank you. Next question and a comment. This equipment can help those who do well counts following an oil spill. Can this be used for counting dolphins as well? Can it pick up the dolphin clicks?
It does not. It's not acoustic, so it does not pick up clicks. And it would be difficult to use it for counting dolphins because typically what we see, you could, if it depends on how finely you want to count the dolphins. If you want to know that there's, a group of dolphins at a particular location and about what the size of the group is, you could do something like that with it. But if you're trying to get an accurate count of the number of individuals, it's not going to show up that well because typically what you see is a disturbance of the water and as a human seeing a group of dolphins, you basically see a lot of splashing and bodies coming up, and it's just not going to be able to keep track of all that and get an accurate count.
Gotcha. That kind of leads to the next question. Does separating detections fall apart when you have pods of whales or beluga or dolphins?
Separating, I'm not sure what they mean by that.
I am assuming what they mean is separating out either blows or disturbances to mark an
Uh,
individual animal.
so I'm still not what the question is. Uh,
That is
so
a-okay. We can send this to you separately offline.
okay.
I'm going to move to the next question. Um, is SWIR better at dusk and night?
It is not better at night, unless you have some sort of, external light source. And at dusk, I think SWIR is the condition where it potentially is better is if you were having to go through, certain types of atmospheres where there was a haze, such as that one example I showed. But generally, Longwave IR is going to do better at night because it's relying on the more of an emission rather than a reflected energy. And so, yeah.
Gotcha. We do have a follow-up from that previous question. What they meant was if you have a large number of blows for many individuals, how do you come up with a good estimate of numbers of individuals?
Okay. So a large number of blows is not a problem as long as they're not all clustered together. And so one of the things we have seen at Granite Canyon is when we get a very large group, it'll just look like, a Las Vegas fountain. There'll be blows all over the place, and you'll have one blow that obscures another blow. And so when they're closely spaced and there's a large number and they're all happening simultaneously, yes, that's a challenge. And yeah, we're going to miss some in that case. If it's a large group and there's enough spread in them, and these cameras can see pretty finely in angle, in range, not so much. So if they're lined up in range, one's going to obscure the other. Then you can do a pretty good job of it, and the computer doesn't really care that there's a large number of blows happening, right? That's more of a challenge for a human because they have to kind of do it right there and in real time. So the nice thing about a system like this, especially with recording the video, you can even play it back and have a human look at it and do a determination after the fact. But yes, it is more challenging when there's lots of blows that are close together, and that's the key. Is they're close together and they obscure one another, then that makes it a challenge.
Great, thank you. We do have a few more questions. Can you track or determine a whale's orientation or direction of travel? I'm assuming with the recording of everything, a human could do that after the fact, but if you want to answer that.
Yeah, so the system that I showed the map display, that's basically what it does. Is it'll get a blow and then it will attempt to associate future blows with that same blow that you saw. And at Granite Canyon, most of the whales are either going, north to south or vice versa. And so you kind of know what path they're generally taking. And so it makes the problem easier. Now, occasionally they get whales that will just kind of hang out in the area, and that makes it a little more difficult to track them. But yes, there is a process for tracking the animals, and that's important for determining how many animals there are because you're making assumptions about their respiration statistics, and so you want to associate that same all those blows from the same animal together or same group of animals so you can accurately make that determination.
Great, thank you. Next question. What sea state conditions do detections become too problematic?
Yeah, so the thing I usually tell people is it kind of equates with a human watching. If it's when it starts to get hard for a human to see the whale blows, and this is of course during the day, then that's about where the system also starts to struggle. And so that's typically around a Beaufort 4, Beaufort 5, maybe, depending on other factors and how big the blows are and so forth. That's typically the conditions where I think humans start to have problems, and that's where the system starts to break down as well. Of course, the real advantage is at night it works even better than during the day, and so and that's where, of course, humans can't see.
Gotcha. Okay, next question. Have you used different optics for different ranges to try and maintain a consistent pixel on the ground resolution?
No, we haven't done that.
Oh, Kevin, I see that you are muted. Either you self-muted by accident or something.
Can you hear me now?
Yes, I can hear you now. Sorry.
Okay. I don't know what muted me, but.
Okay.
Well, I said no to that question. We
No,
haven't
no to that question.
done that. Yeah.
Awesome. Okay. Couple more and we're going to wrap up. Where or what are they going to be doing in Canada?
We're going to be on a vessel and basically testing the system. There's going to be a group of we're going to have humans observing as well as the camera operating, and we're going to review the video and run the system in real time and basically look and see how well it does up there.
Great. And I'm going to grab this one last question. Any other questions I'm going to send to you offline after we wrap this up. So the last question is, can you forensically ID species?
Well, that would be up to the machine cannot. And then the question is, can a human do it in looking at a video? I think if they have contextual information, if you're at a certain location and you're seeing a whale go along the shore and so forth, you probably have a good idea of what it is. So I think to some extent, but I would say it's to the limit is the ability of a human watching a video to ID the species. The machinery cannot ID a species by itself. It doesn't do that.
Mm-hmm. Gotcha. Following up to the Canada question, what species are you looking for in Canada?
I'm not sure actually what species. The biologist could answer that better than I could. I don't know. I think that it's more we're not looking for any particular species. We're basically going to be operating on a vessel and looking for the ability to detect any species of marine mammal that would be approaching the vessel. So it's not any particular species.
Okay, is this the east or the west coast of Canada?
The eastern area.
Wonderful. Kevin, do you have your email somewhere on these slides that we can show to folks online?
I do not, but I'm fine with giving it out. You want me to give it to you now?
Yes, if you could verbally spell it out for everyone.
Sure. It's K Sullivan, and that's KSULLIVAN at Toyon, TOYON.com. And we have a spam filter, so if I ignore your email, it might be because it's in spam somewhere. So you can try again, I guess. Sometimes it happens, sometimes it doesn't.
Great. I will forward on any questions that we didn't get to, Kevin, and thank you so much, everyone, for joining us today. I'm going to give you back 7 minutes of your hour.
Okay.
Thank
Thanks for the
you.
opportunity.